Carr up here at the university. Pete and I go way back, way back. Certainly on your time scale, but it seems like only yesterday to me. I did my graduate work here at the University of Minnesota, so I was where you are now, but that was a long time ago. I came here in 1967 after getting my degree at Oberlin College in Ohio. And in my third year, I was doing electrochemistry. In my third year, Pete came here on a job interview. Now, Pete's a couple of years ahead of me in life. So I was a graduate student, and he was looking at a job here. It turned out that the job didn't work out for a number of reasons, none of which related to Pete's ability or quality. It had to do with other things. But as in the interview, in between stops meeting important people, my research boss brought Pete up to the laboratory. I was a third-year student, I guess I said. And he said, Larry, I gotta leave Pete here for about 45 minutes. Why don't you tell him about your research? Now, this kind of thing happens. So you're all graduate students, so I want you to know that it would be good for you to be able to do such a thing when somebody drops into the laboratory. It's really an important skill. And you know, you just get over the anxiety of it. But Pete sat there in a chair, and I was up at the blackboard, and I was drawing voltammograms. We were both electrochemists. And that was the first time I met him, and that was in 1970, I think, or 69, not sure which. And then he finally ended up at Minnesota in 1977, and came here and moved his research group here. And of course, we got together right away because we were pretty good friends, and we also had very similar interests. He was still doing electrochemistry back then, as was I. But I'd taken the route of a liberal arts college career, and he had taken the route, the path of a research career in an R1 institution. So we've been friends ever since, and really very good friends, both scientifically. I've published 3 papers with him, and personally. So it's tough what he's going through. He had a disc rupture in his neck, pressed against his spinal column, and partially paralyzed his right arm. He had to have surgery to repair that, and apparently the action in his right arm is coming back to normal. He's making some progress. I'm going to see him this afternoon. And it kind of throws you guys into a little bit of disarray, a little bit of chaos, because we're trying to keep the course going even though Pete can't be here. Let me tell you that you're very fortunate to be working with Pete. His international reputation in chromatography is really superb. So he is a very important authority in the area of chromatography. I mean, I can't get close to him. I'm a neophyte in chromatography, and he's the experienced older gentleman. You wouldn't like to hear that, but so now the last 2 days you had Professor Dwight Stoll here, right? Now Dwight teaches at Gustavus Adolphus, and in fact Dwight has the job that I used to have. Okay? He beat me up and took my job. It was terrible. And Dwight was a student of Pete's and did a tremendous amount of work in the development of Pete's program in 2-dimensional HPLC. So you were, again, hearing from, you know, an extremely competent chromatographer the last couple of days. Okay, so I was at Gustavus. Dwight is now at Gustavus. The guy who's going to follow me is a guy named Joe DeLay, who is in charge of the mass spec facility here at the U, and he's going to talk about mass spec detectors and how they hook up to chromatography equipment. And interestingly enough, Joe was a student of mine at Gustavus in the early 1990s, who went on to Wisconsin, got a PhD, worked in industry for quite a while, and now is settled down at the University of Minnesota. It's kind of spooky, isn't it? Yeah. Oh. This is because I don't have my power supply. I think we'll make it. I did see some notes on your reports, your 1-minute papers, right? And just something I want to pick up. There are some issues, just like when I was a graduate student and my class got together. We all came from different backgrounds. The core of us were really devoted analytical chemists, and we had a lot of material in undergraduate because we sort of selected that direction for ourselves. But the students from other areas like food science and engineering had some holes in their backgrounds because they didn't take the same courses that we took as analytical chemists. And that's part of what I see in the questions that you're asking. So those of you who are having trouble with some very basic ideas, like signal to noise ratio and digital filter treatment and that kind of stuff, if you haven't seen that before, go find an undergraduate instrumental textbook, like Skoog and West, that kind of book. Or go to Google and type in a question about signal to noise and see what you come up with, all right? It's not very sophisticated, not very difficult, and it's dealt with mostly in undergraduate courses, but some of you weren't exposed to those courses, and I understand that completely. But something that is fair game for us to spend a little more time on is the method of evaluating baselines in chromatography. Now what we have here is something from a guy named Bicking, who's a chromatographer here in the Twin Cities area, actually. And here's the citation for it if you want to take a look at this. This is LCGC North America. And there's also a Europe edition. Some of the articles are the same, but not all. And this is volume 24, number 4 in 2006, from about April of 2006. There's a nice article. Well, nice. And some of you will be put to sleep by it, but because some of these things can get a little bit annoying that way. But let's take a look at the situation here. What Bicking did was to take and simulate Gaussian curves, right? Symmetrical Gaussian curves with a standard deviation that's easily calculated by statistical methods which you're aware of. And then bring them close together here in different heights. So that complicates things, but with a resolution factor of about 1. What's the resolution factor, RS? How do we calculate that? Have you seen that? Mm-hmm. Off the top of your head? No.
2 times the difference in retention value over time? No.
Or the sum of the widths.
Yeah, sum of the widths.
Yeah. Another way to think of it is the difference in these 2 retention times, that's this gap right here, divided by the average width of the peaks. That average width, width plus width over 2, the 2 pops up, so 2 times this. So that's the same definition. I just find it easier to remember divided by the average width. It's sort of intuitive. Okay, so how does the computer deal with this in the best way? So this is a method called a baseline drop, and it just goes from this minimum point and drops straight down, and then everything to the left is integrated with this peak, everything to the right is integrated with this peak. It turns out, even though this looks like a really ugly thing to do, it's remarkably good. The star up here means it's actually the preferred method. There's a second preferred method down here called the Gaussian skim. And that's not milk, that's right, skimming the line. So with the assumption here that we have indeed Gaussian peaks, we can extend the Gaussian peak down below and then integrate everything under the Gaussian peak and everything under this little Gaussian peak. And those are the 2 areas that we work with. This is another good choice. Minimizes error. 2 that have more error involve, first one is the use of the valley technique, where you take a straight line and go from the foot to the valley and then from the valley down to the foot of the second one. This has the effect of underestimating both areas. It is a choice in chromatography equipment, in the software. And then the exponential skim where you take an exponent term here and you assume that this is an exponential decay rather, and then take this area and this area to do the calculation. And when you're dealing with nice Gaussian peaks, this is not a particularly good approach. But I think it's fair to say that you don't always work with Gaussian peaks. And in some of the consulting work I've done with a pharmaceutical company, we see peaks that look Gaussian up front, but then tail way out. And this is closer to an exponential tail, okay? So I think you can see if you've got a peak down here, it's going to look together it might look like that, and probably the exponential with a big tail. Generally though, if you want to stay within 1% or 2%, the Gaussian skim or the drop And the computer does this automatically. Nobody does this by hand. Okay, it's in the software. I mean, thank God. You'd spend all your time messing with data analysis. Is that clear? You got a question about this? Does it make sense? You see it both, of course, in gas chromatography and HPLC, and other kinds of chromatography in between. It's very common. All right, well, let's get to the point. Oops. Misfired here.
Just go back. The arrows? All right.
No, that's completely backwards. I'm sorry.
You want to click on the actual slide, the number 1 slide? and
But
then-
I'm trembling here for some reason. Yeah, double click on number 1 slide. There we go.
And then do the PowerPoint.
There we go. Okay, sorry about that, folks. This is an outline for today. We're going to be talking about instrumentation. We're talking about stationary phase particles. We're going to be talking a little bit about the surface chemistry on those particles, and then describing some variations on the theme of high-performance liquid chromatography. Oh yeah, here are the 1-minute papers. This is my email address, hotzagustavus.edu. If you would like a copy of the PowerPoint that I'm going to show here, because there's equipment that I'm going to show you, send me a note asking me for the PowerPoint, and I'll send it to you by return mail, okay? It's not top secret or anything. Here's a classic no instrument experiment, mostly put up here because the colors are pretty. We're going to take a complex mixture, colored black here, we're going to put it into a column, load the top of the column. The column has stationary phase particles. For this kind of chromatography, where we're relying on gravity to move the mobile phase through, the particles are going to have to be pretty large so that it's possible for the fluid to flow around the particles. If the particles are real small, the fluid will take a lot of time to get through. If we can't wait around for several days for the fluid to get by the small particles, we may have to apply a pressure. And that was the beginning of high-performance chromatography, applying the pressure to force the liquid through the packing. The larger the packing, the poorer the ability to separate these colors. Okay, so we loaded up here with this black material that contains 3 components, yellow, red, and blue, and we start eluting with solvent. Now, I'm going to describe for you what we call an isocratic experiment, which means only one solvent. Okay, now the solvent will follow this, and the solvent will pull along and displace the various colored materials. The material in this mixture that is least tightly bound to the column will move out first, and it will elute. And then we continue to use the same solvent, and we cut this one off when we see the end of the yellow, and then we elute the red, and then continue with the same solvent, we elute the blue material, so we can separate the dyes that way. It's one solvent. It may be an aqueous buffer, it may be methyl alcohol, it may be 50-50 aqueous buffer and methyl alcohol. Whatever it is, we use that solvent all the way through the experiment. It's isocratic, that's called. Okay? Now, what are some of the problems here? I think you can see right away that these separations are not very distinct. What that betrays is a lack of efficiency in the separation. The ideal separation would be that as we added mobile phase here, we pull the yellow away and there'd be a white band in here before the red started to pull away. You see that? So we'd have a clean separation of the materials. Clean meaning, in this example, down to baseline. We'd get one batch out, and then we'd have some dead space, and then the second batch would come out, and so forth. That would be the clean separation. That's a matter of separation efficiency. Okay? The other thing we could do here is to use different solvents. So We would start out with a solvent that would be a very strong solvent relative to the yellow material, so it would displace it very easily. Then we change the solvent mixture to push the red material through, because it would be, if we change its strength relative to the yellow, make it stronger, the red will come through, and then make it even stronger. So what we do then is change the solvent, and that's called a gradient solvent experiment. And in this case, it's a step gradient, not a straight line. It's a set of steps of solvent strength. To make these things sharper, what we would want to do is to use smaller particles. Smaller particles have higher surface area, so that the contact, the chemical reaction between the colored dyes and the material is more efficient, stronger reaction. Okay, so there's no instrument there. Now here's probably the oldest picture that Pete could find of a simple isocratic LC system. Now, you can use mixed solvents. It doesn't have to be just water or just methyl alcohol. It can be something mixed up 50-50, something like that. Whatever it is, you don't change it, okay? And you take that solvent from the reservoir and you fill it with a pump and push it. Take it through an injection loop. You'll see more of this next time we're together. And then press the material through the column to a detector, to a waste container. The detector picks up a signal, and back when this was a real good example, a strip chart recorder would take the detecting signal. Okay, so this is real primitive. This is like 1960s technology. But then I'm 1960s. Actually, I'm 1940s technologies. Okay, so here, that's a simple LC system. Let's jazz it up a little bit and protect it a little bit. There are some prices to pay for being careless in HPLC. And what we want to do is to put in a few devices that will make our lives simpler and make it possible to extend the life of the column. It's a practical matter. As you'll see, columns come in a variety of sizes, but the least expensive of them cost a couple $100 a piece. So this is something that you don't want to just throw away by carelessness. Protected here, once again, it's isocratic, so we have a mixture of solvents over here. And we have a pump. This is supposed to be connected, but it isn't. This is the pump even. And then in older devices, if we're using, say, a silica HPLC column, just silica particles, we would put in something called a saturation column, which is also silica. The idea here is that silica can be quite soluble, especially at basic pHs. pH 8, 9, 10. Silica becomes pretty soluble. You don't want, over a series of several dozen chromatographic runs, you don't want your silica to dissolve and go out to the waste. So one of the early tricks applied was to pre-saturate the solvent stream with silica from a column that you could just throw away when it was depleted. And then you'd saturate the a few hundred parts per million silica, and it would keep this from dissolving so fast. So that's what that is. In addition, a guard column to pick up junk from the solvent, or to pick up junk from the sample. Okay, there may be some things in the sample that will have such a high affinity for the column that they'll grab on and will be very, very hard to remove. In fact, if you take a look at an industrial column, somebody that's been doing analytical work in industry, after a few months, you'll probably find all sorts of things that are essentially permanently welded to it, all right? Chemically welded, not physically welded, but chemically welded. An example that comes to mind. A number of years ago, I was having students use isocratic HPLC to analyze for caffeine and a couple other things in soda pop and coffee, right? They were doing an isocratic method, and they were working in the springtime. At the end of the semester, we just shut down the instrument for the summer, and when I went to get it working again in the fall, I said, no, I'd better clean the column just in case. And so I used a strong solvent, right, like 95% acetonitrile, and out came the dye from Mountain Dew. You know, that weird yellow. Yeah. It's like, really grips hard. So you don't want that on your analytical column. When you tie up sites on the analytical column, you drop the efficiency of the separation of the column. You get wider peaks and shorter retention times, so the peaks will cluster together and get fat. You don't want that. So you take out things like those, like the Mountain Dew dye, and get it out of the way beforehand. So that's a guard column. And then down here, we have to have a back pressure device. All this does is, if in the detector, so you've got an optical cell, and you've got a pressure drop from the column down to the outflow here. So this is atmospheric pressure down here, and this is, 300, 1,000 psi, something like that. You're going to get an air bubble forming in that optical path. Cavitation occurs, right? So it's the low pressure will allow the gas that's trapped in the solvent here to expand and form a bubble, and then you get a bizarre signal coming out of the detector. Actually, you see the bubble shrinking and growing as the pulses come through, so you get a zigzag kind of outcome. So a device to pinch this off, to move the pressure drop point down to here and away from the detector. It's another guard for the system. Okay, so now let's move away from isocratic separations to gradient separations. And we're going to make this, I think you can see why Pete chose this, even though it looks pretty primitive. It's sort of laid out in blocks. Here we have two solvents. And we control the mixture of the solvents through this controller unit. So we change the rate at which the pumps pump. The streams come together in this thing called a mixer. The streams come together and they have to be mixed up intimately, all right? And then that solution goes and picks up the material from the injector, and then the separation occurs on the column and so forth and so on. And this shows a fraction collection as well. We can collect the fraction holding each peak if we want to, or groups of peaks in test tubes, and then do another separation or do what we want to do with them, all right? So you can control the mixture by setting the controller to change the pumping speed. Now, there are some problems attending this, and that is when you mix the two solvents together at the mixer, and I'm going to make this point again on Friday when I'm here. When you mix these two solvents together, if you haven't removed the dissolved air from these two solvents, you can have a catastrophic air bubble situation develop. Turns out that water has very low dissolved air concentration. It's pretty polar. Most air molecules are non-polar, right? Nitrogen, oxygen, the big ones. Carbon dioxide, non-polar. So those things really like low polarity solvents. If you mix a lower polarity solvent with water, what's going to happen? The air comes out in bubbles. If that happens in the mixer, you're going to have an embolism, and your instrument will die of the bends. You won't be able to get this. You'll get bubbles into the column, you'll have cavities form. It's horrible. So you have to do something to remove the air up here before it gets to the mixer. Just keep that in mind. We'll see that technology next time. In addition, I want to point out that the distance here from the mixer to the head of the column, okay, is called the gradient delay time. If you start with a particular mixture here and run that through, and then you tell the controller to change the gradient, the controller will change the amount of material that comes to the mixer by pumping at different rates. And this will get mixed up. You may think that when you tell the gradient to start, that actually the gradient is starting up here, but in fact the gradient starts down here. So there's a time delay between the right mixture that you want to have, and the mixture that the column is being immersed in. You follow that idea? So that's called the gradient delay time. We're going to see that again. I'm giving you a little preview of coming attractions. Are we okay with this then? Any questions here? It's pretty straightforward. Huh? Hardware lecture, you know. Pretty straightforward. How do you think, this is a ternary mixture, so there are three solvents here, a controller to mix the three solvents together. How do you think, and this is the two, and look at remember the gradient delay time from the mixer to the column? Compare that gradient delay time with this gradient delay time. What do you see? We're bringing the solvents together. We're using the controller to set these selection valves. So we put the mixture together, we do the mixture up here, and then we pump it so it's mixed at low pressure. Right, so this is low pressure mixing. Then we pump it into the injector in the column. What's the delay time here? The delay path, sorry. What's the delay length? From here all the way over to here. That's a much bigger delay time. Now in these kinds of devices, that delay time, depending on the flow rate of solvent, that volume will be 1, 2, 3, 4 milliliters. All right? And in some experiments with larger columns, it doesn't make any difference, really. You still get a good separation. But if you're working with a small column, a micro column, you can get really serious surprises this way. If you're running 100 microliters per minute through the column, 100 microliters, 1/10 of a milliliter, and your delay volume is 2 or 3 milliliters, you got to wait 30 minutes for the gradient to get to the column head. I mean, if you like long coffee breaks, that's terrific. You know, you inject the thing and you set the gradient. Oh, I got a big mixing time here. I'll go get a cup of coffee. Terrific, but it's very inefficient that way. Contrast that with a case where if you have 100 microliter, 1/10 of a mil per minute flow rate, and this is from say here to here is your only delay path. Then you can do that. Then you only have to wait a minute or something like that. Some of these mixers, as you'll see, I'll show you a design on Friday, are very efficient, 75 microliters for a volume. Let's talk about columns. Okay, columns come in a wide variety of sizes. I've shown you some pictures from the internet. I love this. I love Google. Okay, so these are analytical columns. And this is a 5 centimeter column, and a 10, and a 15, and a 20. And these things are 4.6 millimeters internal diameter, and as I said, 50 millimeters, 100 millimeters, 150, and so forth. So these are the so-called analytical columns. They're high-performance analytical columns. The bigger ones up here are prep and semi-prep columns. These may be 2.5 centimeters internal diameter, and as you can see, 20 or 30 centimeters long. So there's a lot more material in here. Okay, a lot less material in here. When we use the right packing materials here for these kinds of things, we get very sharp peaks with good separations. When we use the amount of material in here, we have to use somewhat larger particles. We get poorer separations, but we have a lot more capacity to do separating. Here we use nanogram and sub-microgram quantities of materials to inject into these columns to get separations. Here we'll do multi-milligrams, maybe up to a gram. And here, look at this guy. These are preparatory columns. These would take multiple gram quantities of materials at a time. More about those in a couple minutes. So, difference between analytical and preparative. Analytical and preparative. Now, the dimensions of the column influence the pressure drop, and pressure drop is important. A lot of materials that we use to pack columns can't take more than about 600 atmospheres of pressure. They'll break apart. And then you get little finely divided column materials that clog up the bottom of the column, and then the pressure goes right up through the roof. It's like having a rubber stopper almost at the end of the column. That's a catastrophic breakdown. This Kozeny-Karman equation is an important equation. It's an empirical equation, which means that it's done on the basis of experimental work, not just theory. Of these things on pressure, and plot this out, find the right coefficient. Take these numbers down because I recommend that you spend about 10 minutes doing a calculation here to verify these conditions that I've written down here. 4.5 millimeter inside, 150 millimeter length, 5 micrometer particles, 1 mil per minute with water for the viscosity, you'll find a pressure of about 59 bars, 59 essentially atmospheres within 1% of an atmosphere. Commonly, depending with different solvents, a column like this will show you 40 to 100 bar pressure range. It would be abnormal to have much more than 100 bars on a 15 centimeter column, okay? But you can get a lot bigger results. First, the centipoise is the unit of viscosity, more about that in a second, and that's a millipascal second, and a bar is 10 to the fifth power pascals. Notice we have length up in the numerator, so if we go from a 5 centimeter to a 10 centimeter, what's going to happen to the pressure drop? Double. You can respond, it's okay. Don't be shy. That's when you can't miss out. So if you go from a 5 to a 25, you increase the pressure by a factor of 5. And do you see that if you're not careful, you could accidentally hurt the vacuum material by going above the capacity of the vacuum material? All right, good. So then, and here's the flow rate. You double the flow rate. This is 1 mil per minute. If you go to 2 mils per minute, you'll double the pressure drop. So going to 2 mils a minute, you'd expect double this, or about 120 bars. All right? And let's see, this is the radius of the internal radius of the column. And if we double that, if we cut that radius in half, where am I going here? What's the change in the pressure?
Double it.
Cut it in half.
Oh, great. So quadruple.
Quadruple it, yeah. 4 times the pressure, because this is the radius squared. And this is a very important one, the side of the particle diameter. And there's been a lot of changes in particle diameter over the last 20 years or so. 5 micrometers is pretty much standard for a lot of industrial applications, analytical, quality control, and that stuff. But people are working at the edges now down at below 1 micrometer. Wow, so if we go from 5 micrometers down to 1 micrometer, that's a factor of 5. That increases the pressure by a factor of 25. That's a big change. So we go from, let's say with the solvent combination, 100 bars to 2,500 bars. There are very few packings that can withstand that, so you have to be concerned about that. So what would you do? What would you guys do if you went to a smaller particle? What would you do to compensate in designing? Make that smaller, right? Or put that null down, or make it bigger. Okay. And go to a lower flow rate. So these are compensating factors. It's worth taking a look at the calculations. So a little bit about viscosity here. These are viscosity values in centipoise. I hope you've all had that from PCAM. Oh, God, PCAM. HPLC is really a wonderful combination of physical chemistry, physics, and chemistry. It's a terrifically fertile area that way. So all that physics and physical chemistry you learned, you can apply now. Finally, huh? 1 centipoise for water. Methanol is about half as viscous as water. That's terrific. And the acetonitrile about 1/3 as viscous as water. So if we use water and we get 60 bars of pressure, what happens if we go down to, if we use methanol, we go down to 30 bars of pressure because the viscosity is lower. You follow me? And the viscosity is in the numerator of that equation. If we go to maple syrup, I threw this on to get your attention. That's 200 times the viscosity of water. So don't look for HPLC experiments using maple syrup as a mobile phase. Isopropanol surprised me. This is a fairly structured liquid, even relative to water. It has a higher viscosity than water. And you think that if you would mix water and methanol together, you'd have a viscosity somewhere in between. That would make sense if the universe is orderly. Look what happens. Here's water by itself. Let's follow this line, which is at 20 Celsius. And add methanol. Oh my God, instead of going down, the viscosity increases. And at 50% methanol, the viscosity is like 1.8. Whoa. So if you go from a mostly water mobile phase to a water methanol phase, and you look at your pressure gauge, what are you going to see on the pressure gauge? The pressure's going to go up. It has to squeeze harder because the structural interactions within the solvent called PCAM. We don't have to do the details there, thank God. The structural within the solvent, within the molecules, raises the viscosity. And when we get up to methanol, here at 20, that's that value, 0.54. Okay, so acetonitrile looks a lot like this, but the curve picks up here and then declines more that way. So the bump is lower. So that's the effect. Oh yeah, temperature. While I'm here, what would you guess the temperature effect on the viscosity and therefore on pressure would be? If you heat up maple syrup, it gets more fluid, right? So raising the temperature, so there was a good reason to put that out, not just to attract. You raise the temperature and the viscosity decreases, becomes less, it becomes more fluid. And you can see that here when we go up to 50 and 55 and 60 degrees. So one of the things we can do to reduce column pressure is to run the experiment at a higher temperature. So you raise the temperature. Hell, if it's 50 degrees, 60 degrees is good. Let's go to 150. What do you suppose can happen? If you were a column, what would you do at 150 degrees? Chemistry, you break apart. You have bonds, chemical bonds, you'll see in a minute here, that will break under those conditions, and your column will basically self-destruct. So there are limitations in there. Something about particles. I'm going to move a little quickly here, so these are pretty pictures. These are silica particles. There are a variety of them. Some of them have a very thin coating on the outside with a solid core. These are the pelliculars. They were called that when they were bigger particles. But here, pretty typically, 1.5 micrometers, for example, with just maybe 100 nanometers of, factor of 1% thicker coating. And so the surface area is increased, but the strength of the particle is pretty high. Another thing you can do, and the modern manifestation of this is these things where you have a 5 micrometer particle with sintered nanoparticles on the outside, sintered chemically together, bonded together. You get a very high surface area with strength in the middle. You can also have pores that go all the way through the silica particle, right? And you can also have channels through the silica particle that can improve the surface area of the particle. Surface area is good because that gives you the mechanism for separation. Here's a fused core particle, some pretty electron micrographs. You can see what these are actual particles, so they look like mushrooms of some kind, right? A textured surface. And those are pores, and solvent goes into that, and solute species go into that. They interact with the surface and more or less stay behind as the solvent moves through, so you get an idea of the motion of the solid in here. This is I like this one because these particles are so uniform. Manufacturers now can guarantee uniformities of about 1%, which is amazing when you think about it. So 4 micrometers plus or minus 0.05 micrometers packed together. What's the benefit of that, do you think? Do a thought experiment. You've got a huge room full of ping pong balls, right? And a second room that's half ping pong balls and half basketballs. Which collection is apt to pack more efficiently? The uniform collection, right? The basketballs will create big cavities, and liquid will come through without contacting much of the little particles where the action is. Okay, so uniformity is important, and look how uniform that is. It's quite remarkable. These fused core particles are now a hot item. They're 150 square meters per gram. Think about that. How big is that? 150 is like 30 times 5, 10 times 15. So 30 feet by 45 feet in 1 gram of these particles. Think about the size of that surface. It's enormous. Pressures to at least 600 bars. Manufacturers claim. Quickly, monolithic silica columns, instead of having particles in here, you do a polymerization reaction inside a column made of a polymer material, polymer on the outside, and you do a silica polymerization in here. And you generate this highly textured collection of channels. These are not discrete particles. the whole thing is a particle. So that's what we mean by monolith. The whole thing is a particle. And here the motion of the solvent through the channels takes advantage of the enormous surface area of these. Now these are kind of contentious. These have been the subject mostly of academic research laboratories. Only one company markets them, I guess it's Merck. And there's conflicting evidence in the literature that you really get a lot of advantage out of this. But I'm telling you this to open your eyes to some other things that are happening. These may catch on, like any discipline. Chromatography has its fads. Okay, surface chemistry. Normal phase silica or alumina are highly polar surfaces. About 8 micromoles of hydroxide sites are on the silica per square meter of silica. So see, so we had a gram at 150 square meters. And now we've got 8 micromoles per square meter. So that's what, about 1,000 micromoles in a gram? 1,000, 1,100 micromoles in a gram of hydroxysites. Okay, so that's what, about a millimole per gram. And a gram is what it takes about to pack one of those analytical columns that you saw. So you've got about a millimole of hydroxy exchange sites. So solutes can come in and grab onto those sites and hold on. So that has to do with the capacity of the column. The larger the number of millimoles of hydroxide available, the greater the capacity of the column to do the separation. Okay? So imagine if you have that kind of thing inside one of those great big preparative scale things, just imagine you could have moles of material separating out in those big preps. That's why we call them preparative. Now there's also, here, these are selected for polar species. The hydroxy sites are quite polar. And so polar species adsorb to the surface, cling to the surface by polar interactions. You can also induce charges on benzene rings, aromatic rings, and those can be remarkably sticky on these kinds of surfaces. You wouldn't guess they would be because you associate those with oily materials. But they do stick because of the induced charges. What we call strong solvents here are the solvents that will displace those molecules from the stationary phase. And so those solvents that are strong will be highly polar solvents. They'll come in and push the molecules away because they're so polar. I want that site, get out of here. Right? Follow? Okay. Weak solvents are the ones that can't interfere with that charge interaction. So the weak solvents have low polarity. Now what we're going to do is reverse that thing by chemically bonding an organic phase to the silica. This is bare silica or alumina. And here we can bond the phase to silica or alumina or zirconia, not so much this. This is hard to work with, but mostly silica and a little bit of zirconium oxide, which incidentally was a discovery of Professor Carr and his group here. This is was a major deal. Okay. These things now have organic phases. They're oily. They select low polarity solutes. Low polarity solutes will come up and what we call partition to them, like oil partitions to an oily phase. The strong solvents now are the opposite of strong solvents up here. They're of low polarity, and the weak solvents are of high polarity. So those are very basic definitions for you. Something about the surface chemistry. This is what the surface chemistry of a silicon oxide surface looks like. We reacted with a chlorosilane, just this one, take a look at this. HCl condenses out, and we have a silicon-oxygen-silicon bond that forms. Very straightforward chemistry, very fast chemistry. You mix them together, and the sites get filled. Now, there are 8 micromoles per square meter of OH sites. In the typical bonding kind of chemistry, we'll get about 50% of those sites covered with the bonded phase. 50, 55, 60% at the best. And so there are extra silicon sites, which I'll show you in a minute. Oh yeah, you can bond to one or you can bond to 2 sites like general. It's not general, but it's close. And you'll be left, here this shows The main reaction is this silane with an 18 carbon long chain that's a real oily long chain, right? It's like worse than diesel oil. It's real low polarity. And here it shows these things sticking out into a low polarity solvent. And you have these sites, OH, that have not reacted with anything. These are low polarity sites now, and solutes that have low polarity will try to cling to these. But what happens down here? These are high polarity sites, see? So these sites can cause you trouble. One of the things they can do is they can be a site attack for a base, hydroxide, and this can dissolve away and it can weaken the underlying structure. Please, the sizes are not right. They're disproportional to make it look. So one of the things we can do is to react groups that occupy multiple sites so that we have a lower polarity region. And we can also do something called end capping, which is down here. And this, once you do the C18 long chains, then you treat in a second process step with trimethylchlorosilane. This is typically a chlorine here, chloride. And that bonds these things to the remaining unreacted sites, and you can take another, you may only have 10% of the hydroxy sites left unreactive after this end capping. So end capping is the reaction with a small silane. All right. Now this helps too because these bonds can be hydrolyzed, or these longer bonds over here, and having these end cap groups prevents solvent from getting down here to rupture this silicon-oxygen bond. Base. You're not supposed to use these columns at pH above 8 because the base attacks and can cleave these things and give you degradation of the column. Your nice low polarity phase will then flow out into the trash and you'll be left with a lot of hydroxy sites after a while. So you find that the column efficiency suffers at high pH. The virtue of zirconia is that in the case of ZRO in this bond, those things are much more rugged for hydrolysis, and you can use zirconia columns pH 10 and 11 without any serious degradation. That's why it was a big deal to invent that, incidentally. Let's see, we're just about out of time. So these are popular reverse phases, and I'll tell you what, we can talk about these next time. And actually, again, send me by email something asking for the slides, and I'll send them to you so you can look over this. It's impossible to take detailed notes so you can see the slides. Now, let me just ask you here briefly, anything I can answer for you right now before you try to rate your 1 minute? You got any questions?
Actually, we have a Google Drive, Google folder for this class. So if you can send me a copy, I'll put it so everybody can have access to that.
Okay. And you have, I didn't know about that. Thank you. I'll send it to Devon.
Thank you.
This isn't very challenging, guys. I hope I haven't bored you. I'm talking about now a set of some basic practical knowledge that can get you a really good job if you continue to grow it, develop it. Really, I'm not kidding. Because this technology is so widely used in industry. So widely used. There's a tremendous demand for development of methods. And to develop the methods, you need to know the distinctions between these phases and which phases you choose. And it goes beyond just being able to Google it. You've got to be able to make serious, deep, professional kinds of judgments about these things. So just a big, strong hint. You could become millionaires. Well, 100,000-aires. If you develop these skills and then find a way to sell them, okay? All right, well, thanks for your attention, everybody. And I'll see you on Friday.